Hi everyone, I'm Inam. I'm excited to share the knowledge about design of truss, in which we are studying about the design of tension members. Truss bridges, building, and even your bicycle frame, they all rely on the strength and efficiency of trusses in tension. Today we will delve into the world of truss design, focusing on how these structures handle tension forces. Our focus today lies specifically on truss experiencing tension forces. Understanding how these members behave under tension is crucial for ensuring overall structural integrity. Since we know about the truss, that truss is a structural element that support the axial forces, whether in tension or in compression. So there are two design involved in design of truss: design of tension member and design of compression member. In this lecture we are only discussing about the design of tension member, that how we will design the tension members. Since this is the analysis of the truss, that the red bars red element shows the tension and the green member shows the compression in the truss. So here we only be designing the red element, that are the tension members. So whenever the word design used in every term, so this means that we will satisfy this main design equation, that the design strength should be greater than or equal to the required strength. Since you are familiar about the design strength and the required strength, so how we will calculate that the design strength should be greater than or equal to the nominal strength or the required strength. So nominal strength multiplied by strength reduction factor gives the design strength, which can be calculated by different formulas given by different codes, and required strength can be calculated by the load effects after applying the load factor, etc. So means that the design strength should be greater than or equal to the required strength. Since in this we are also satisfying this design equation in design of truss member in compression, in tension. So our motive is that we will finding this term. So first we will finding the nominal strength Pn and the reduction factor for the truss, and this will be calculated by different softwares or by manual calculation, as we did in structure analysis 1 and structure analysis 2. So means these are the analysis part and this will be the design part. So we are only focusing about this. First we will find the Pn for mean the nominal strength for truss in tension. In compression video we will finding the Pn in compression of a truss member and the reduction factor in truss for tension. Remember this value comes from the analysis part, means structure analysis 1 or 2 or from different softwares. So design of tension member, the tension member may be fail in 1 or 2 limit state. So it may fail in 1 or 2 limit state. Whichever is minimum we will compare with the required strength. So for yielding we had different formula, and for tensile rupture we had different formula. So means we will going this. For yielding the nominal strength will be the product of yield strength into the gross area. Why we use the gross area? If we consider a tension member, means a member applied the forces in tension. So first it may yield reaches to this point. So after this we will get the for yielding we will get the gross area, means the total area, means it will moves, it will deflect, or it will increase in length. So for yielding we will get the gross area. For yielding we will use the gross area, which will be the nominal strength will be the product of yield strength multiplied by the gross area. And for tensile rupture the nominal strength formula will be the ultimate strength multiplied by the effective length. Remember this. Why we will use the effective? Because we are covering the holes, because fracture occur in holes places. Since if it is a member, there are different holes in member, so we will subtracting the holes area from the gross area, and then we will multiplying with another reduction factor to be in safe side. So in tensile rupture we will use the net effective area. Effective area will be equal to the U times of net area. So in next slide we will discussing about net area. So effective area, so it is very crucial. So for this the next lecture will be about the effective area. There are different conditions for the reduction factor used in the net area with to get effective area. So means effective area is equal to AE is equal to reduction factor multiplied by the net area. So in this lecture we are only discussing about the net area. So in next lecture we are only focusing about the effective area, that how we will get the effective area if the members are in welding or in the tensile rupture, etc. So the summary of this slide is that the tension member fails in two conditions, whether in tensile yielding or in the tensile rupture. For yielding, the nominal strength will be this, and for tensile rupture, the nominal strength will be the ultimate strength multiplied by the effective area. Means this is the only difference between the two conditions. Whichever is the minimum, we will compare with the required strength. Then by analyzing, we will submitting the report that whether it may support the load or not. So it's okay or not. Since you know the design equation that the required strength should be less than or equal to the design strength. So design strength is the product of nominal strength multiplied by reduction factor. In last slide we had found the value of Pn in case of yielding and in case of rupture. So what will be the value of this reduction factor in case of yielding and in case of rupture? So in case of yielding we are using this value 0.9, and for rupture we are using this 0.75. In rupture why we are using the less value than the yielding? Because in rupture we are using the ultimate strength which is more than the yielding strength. That's why we are using the 75% of the ultimate strength. Now we are only discussing about the gross area and in net area. What will be the gross area and net area? So the gross area, if we consider this is a member in tension, that forces is applied in this fashion, so the member will be in tension, purely tension. So the gross area means the cross-sectional gross area transfers to the applied loading will be the width times this width times the thickness. So B multiplied T, this will be the gross area. Remember, this gross area means total area without subtracting the area of holes. So what will be the net area? Net area will be equal to the gross area, means the total area minus area of holes. So if this is a failure plane, maybe this bar fell in this holes, so the net area will be equal to the gross area minus area of holes. How many holes in this plane? 2 holes occur, so we will multiply the area of holes with 2. Since we had 2 holes, so we are finding the area of holes multiplying with the number of holes, then gross area minus the total area of holes, we will get the net area of holes, means net area of the cross section. For net area we had 2 conditions, whether the holes are in parallel condition, parallel holes, or in staggered holes. Why we provide the staggered holes? When the length of the holes are welding are not sufficient to provide the holes in parallel condition, then we will using the holes in staggered condition. Means if this is a member, so we will providing the holes in this term. These are the holes, so we will providing the holes in this term, not in parallel condition. So what will be the net area in case of parallel hole and in case of staggered hole? So the net area in case of parallel hole means these are holes are parallel in one line, so in one line but in same direction. So remember this, the net area will be the gross area minus area of holes. So the area of holes will be this, that the diameter of a hole plus the tolerance. We will add the tolerance whether it is 1/16 or 1/8. So we are adding the tolerance with the dia of the hole into the thickness. We will get the area, and n represent the number of holes. How many holes occur in the failure plane? Then in this case the n will be 2 because the failure plane is in this. So the total number of holes will be in this failure plane is 2. So this will be the net area in case of parallel hole. Remember this, in case of staggered holes, the two additional factor will be added, the staggered length and the gauge length. What is the staggered length? The distance between the center to center distance between two nearest hole is called staggered distance, and G is the gauge length. In the transverse, it is the force applied in this direction, so the transverse center to center length between the two hole is called gauge. So the net area will be this, that the gross area minus the area of holes in failure plane. Remember, this is the area of holes in failure plane. Then we will adding this additional factor, that summation of s square divided by 4g into t. So in this, what will be the n? If the failure plane is this, that is the failure plane, so the total number of hole is 3. 1 2 3 3 here the number of hole will be 3. So what will be the summation? Means total we will add the 1 2 3 4. So it depends on the curve length or the inclined length. Since here 1 2, if the failure plane is this a b c d e, means if this is a failure plane, so the inclined paths are 2. So this will be summation, instead of summation we will use 2 s square divided by 4g into t. So this will be the staggered holes in case of parallel. In case of staggered holes, the net area will be this. So next lecture will be about the effective area. Effective area is equal to u times the net area. Remember this, u times net area. In net area will be changed for parallel holes and for staggered holes. So next lecture will be only focusing about this. So thanks to everyone. Allah Hafiz.